Hello folks, today we're going to do an example of vector algebra in 3 dimensions. In this example problem, we have a biologist who is tracking the migration of some species of whales. And at position 1 at a particular moment in time, the whale is located at a horizontal range of 4.20 kilometers, 30 degrees south of east, and a depth below sea level of 750 meters. At some later moment in time, the biologist tracks the whale and notes that the position of the whale with respect to their radar station is at a horizontal range of 2.60 kilometers, 20 degrees north of east, at a depth of 500 meters. In this problem, we want to find the displacement vector for the whale, and that is the change of the whale's position from time 1 to time 2. All right, so the tricky thing about this problem is that we're working in 3 dimensions. So I'll show you a trick on how to make a rough sketch in 3D, and then we'll break it up into a 2D plus a 1D problem. All right, so let's get a rough sketch in 3D of the position of the whale at the 2 moments in time. I'm going to use Cartesian coordinates, x, y, and z. My z coordinate is going to be up, and then I'm going to have x pointing towards the east and y pointing towards the north. So here is my x coordinate, and that will be east. In 3D, this will be my y coordinate, and that will be in north. And so the way to visualize this is this xy plane is actually horizontal, flat, but we're seeing it in perspective. And so this is the z direction, that is up and down. And let me extend, since our whale is below the sea surface, let's extend the z-axis to much bigger negative values. All right, so there's our 3D perspective, our 3D coordinates. It's going to also be helpful to think of just the 2D position of the whale, that is looking from the top down. If we're looking from the top down, what the position of the whale is, we're not going to worry about its depth. All right, so from that perspective, in a 2D perspective, here is my x coordinate, which will be east, and I'll write my y coordinate here, which will be north. And this way we're going to ignore the depth of the whales. Okay, so let's make a quick sketch of the position of whale number 1. 420 kilometers is the horizontal range. Horizontal in this case doesn't mean along the x-axis. Horizontal in this case means in the xy plane. And so we have 30 degrees south of east. So let's first go to this diagram. Here's north, here's east. 30 degrees south of east. The second direction is your primary direction, so east, and we're going to go 30 degrees south of east. So here's east, and we're going to go 30 degrees south of east. So this is 30 degrees, and so there's east, and now we're going south of east. And that's the position of the whale, the 2D position of the whale at time 1. So I'll write that as vector R1. And this distance, the horizontal distance, is 4.20 kilometers. A little bit later, the whale is 20 degrees north of east. So here's east. We're going to go 20 degrees north of it. So that will be, and at a distance of 2.6 kilometers. So that's going to be, say, right here. This is 2.60 kilometers. And this angle right here is 20 degrees. Make this a little bit darker. And that is the location of our whale at time 2. And again, this is just the 2D plot. It's helpful. It's good to draw the 2D plot first and then try to visualize it in 3D. So again, in 3D, here's our XY plane. This right here will be position 1. And so this is, again, think of this as 2D, and now we're going to go down in depth. Okay, so this angle right here, that's 30 degrees. And this angle is now not down, it's actually coming towards me. And then this is the depth below sea level. And so in 3D, the position of that whale at time 1 is this vector. Let me use a different color. All right, so that's R1. That's the three-dimensional version of R1. All right, so think of this as, this is the distance along the surface, and then we go down 750 meters. In position 2, right, now we're going to go north of east. So we're going to go 20 degrees north of east. Not quite as far. And then we're also going to go down in depth. And so let's say we're down here at 500 meters below the surface. And so that vector looks like this. All right, so that's the position of the whale at the 2 different times. Okay, so now we want to compute the displacement vector. The displacement is a vector that connects position 1 to position 2. All right. Another way to think about it is a displacement is a change in position. You're displacing from one position to the second position. And so our displacement vector connects position 1 to position 2, so it's going to be this vector right here. That's our displacement vector. And in 3D, it's going to be this vector right here. And so what we want to do is we want to compute that vector and compute the distance or the magnitude of that vector. Okay? So now we want to work with vector components in 3D. The method we're going to use to do that is first we're going to compute the XY components of the vectors, which is the horizontal position of the whale. And then we're going to just treat the depth below sea level as the third component of our vector. Okay, so let's write position vectors in Cartesian coordinates for each of the positions. Let's look at the 2D position first. I want to write vector R1 in terms of some amount of I hat. Remember, I hat is the unit vector in the x direction, and j hat is a little arrow that points north. So I hat is a little arrow that points east, j hat is a little arrow that points north, and we want a certain number of little I hats in the x direction plus a certain number of I hats in the j hat direction. So looking at, here's our vector R1. We want to break this up into 2 pieces. Okay, so we can break this R1 up into 2 pieces. You can either do x then y or y then x. I'm gonna do y first. We can go down a certain amount in y and over a certain amount in x to get to position R1. Okay, and so we want to figure out, this is the y component of that vector. This is the x component of that vector. All right, so I'll label this as R1, the x component, and this is R1, the y component of that vector. All right, and now we'll use trigonometry to figure out what R1x is and R1y is. So this angle right here, I'm going to call that theta 1. Theta 1 is 30 degrees south of east. Thinking in terms of the unit circle in our normal conventions in trigonometry, another way of writing that is negative 30 degrees with respect to the plus x-axis. Remember from trigonometry that if you go counterclockwise, we consider that a positive angle. If you go clockwise, we consider that a negative angle. And so R1 is 30 degrees clockwise from the x-axis. So we're going to consider that a negative angle because it's going clockwise. So it's negative 30 degrees with respect to the plus x-axis. When you use the unit circle notation or your standard notation in trigonometry, the x and y components are very simple. The x component is cosine, the y component is sine. So I can write vector r1, or at least the horizontal part of vector r1, as the distance 4.20 kilometers times cosine of negative 30 degrees. And so this is the x part of that vector, plus the y part of that vector, which is the distance, 4.20 kilometers, sine of negative 30 degrees, j hat. Okay? And so plugging in these numbers, in the x direction, we have 3.637 kilometers I hat. I'm going to keep an extra unit of significant figures. Usually when you're doing intermediate calculations, you want to have a little bit extra in terms of the decimal places, and you round off in the end. And if you do sine of negative 30 degrees, that's going to come out to be a negative number, and this is going to be negative 2.100 kilometers j hat. And that makes sense because we have a positive x value and a negative y value. And let's look at this position R1. We can see that it's on the positive x side, but it's on the negative y side. So that's how we know. It's always good to check the signs before proceeding. And so that's the horizontal part of this vector. Now we want to add the fact that it's below the C surface. We're going to treat downwards as negative in the z direction. So I'm going to add on to this vector. So this is just the horizontal part. The total position vector for R1 we can write as 3.637 kilometers I minus 2.100 kilometers J. And I'm going to write it as minus, I'm going to convert 750 meters to kilometers, minus 0.750 kilometers K hat direction. K is a little arrow that K hat is a little arrow that points up. Negative K hat is a little arrow points down. So this means we're going 750 kilometers down. Okay. All right. Now we just need we can quickly repeat this for the second position of our whale. And so I can write R2 equals, at least for the horizontal piece, here's R2, here's 2.6 kilometers, 20 degrees north of east. I'll come over here and write theta 2 is 20 degrees north of east. In terms of our unit circle, that's 20 degrees in the counterclockwise direction, so that's a plus angle. So another way of writing this is plus 20 degrees with respect to the plus x-axis. All right. So before you do vector components, you always want to use unit vector notation or your trigonometry convention for the angles. So R2 is going to be 2.60 kilometers cosine plus 20 degrees I hat plus 2.60 kilometers sine plus 20 degrees. This is j hat. And then we can tack on minus 0.500 kilometers k hat for the fact that we're below sea level. And if I just calculate those on my calculator, we get 2.443 kilometers I hat plus 0.889 kilometers j hat minus 0.500 kilometers k hat. And so there we have it. We have the two positions of our whale. Okay, we're continuing our example of computing a displacement vector in 3 dimensions. In this problem, we have a biologist is tracking the location of a whale, and we calculated the position vector in Cartesian coordinates for the position of the whale at time 1, and this is the Cartesian representation of the position vector for the whale at time 2. And so now we're in a position where we can calculate the change in position, or the displacement. So I will write that vectorially. I'll write that as the change in the position of the whale is equal to the position at time 2 minus the position at time 1. Again, that's the definition of a displacement vector. Displacement is a difference or a change in position. Okay? Graphically over here, I'm representing at least the 2D part, the horizontal range part of the position of the whale, and the K component or the Z component is depth below sea level. But here I'm just plotting the 2D position. Here's the position at time 1. Here's the position of the whale at time 2. Graphically, a displacement vector is going to connect the head of the first vector to the head of the second vector. So that's going to be, this is the displacement vector. You go from the head of the first to the head of the second. Okay? And we can verify that this is the correct vector relationship. Before we do the vector algebra, let's verify that this is the correct vector relationship. Another way to check that is to remember that when you add vectors, you're going head to tail, head to tail. So let's look at this picture again. And if we follow the arrows that follow one right after each other, here we have R1, and then it goes into delta R, and that takes us to the final position R2. Another way to write this vector relationship is to say position R1, we follow this arrow, and we follow it into, head into the tail. We follow it into this vector, so that's plus delta R, and that ends up at the same location as our second position, R2. And so we can see, we can rearrange this, and we can get delta R is again R2 minus R1. All right, so it's always good to check the vector relationship. All right. All right, so it's easy to subtract the vectors once we have them in with Cartesian unit vectors. We can just subtract R2 minus R1, and remember that you have to subtract component by component. You can only add or subtract I hats with other I hats. You can combine J hats with other J hats and K hats with other K hats. Okay, so let's do this subtraction. Delta R. We're going to focus on the X components first. We're going to do R2 minus R1. And when we do that, we're going to get negative 1.194 kilometers. That's in the X direction, or the I hat direction. Now we want to subtract R2 minus R1 for the Y component. And so when we do that subtraction, we're going to get plus 2.989 kilometers J hat. And then finally, we're going to, again, do R2 minus R1 in the Z direction. And we're going to get plus 0.250 kilometers k hat. So that's our displacement vector. And let's just check the signs. It's always good to check the signs before proceeding. All right, so this says that the whale moved in the negative x direction, right? And let's check our diagram. This arrow, if you look at the x part of that arrow, this arrow right here, it goes up in y, plus y, and over in x in the negative direction. So that makes sense. So that means we expect the x part of this displacement to be negative. The y part of this displacement, it's pointing up, it's positive, and so we can check. The x component is negative, the y component is positive. And we can see that the displacement in the z direction is positive, and let's see if that makes sense. Initially, our whale was 750 meters below the surface. A little bit later, it was 500 meters below the surface. So it moved up 250 meters in our time interval. It started low and it went higher, so it moved up, and that makes sense because here we have a plus 0.250 kilometers or 250 meters. All right, so that's our displacement vector. To get the distance, we want to take the magnitude of this vector. All right, and magnitudes, all we want to do is use the Pythagorean theorem in 3 dimensions. And when we do the Pythagorean theorem, since we're going to square quantities, we don't have to worry about the signs. We can just do 1.194 kilometers squared plus 2.989 kilometers squared plus 0.250 kilometers squared, and then we do the square root. So we're just doing the Pythagorean theorem. You're taking the individual vector components, you're squaring them, you're adding them up, and then you're doing the square root. And when we do all of that, we get a distance of 3.23 kilometers. So in that time interval, our whale has moved 3.23 kilometers from position 1 to position 2. The final thing we want to do is we want to calculate the angle of our displacement vector. And so here we can see this is our arrow, this is our displacement vector. Before we get to the math, we can estimate it. So first of all, we can see right off the bat that it is, it's pointing mostly northward, but a little bit west of north. So we're going to expect at some angle, some small angle west of north. Okay. Now we want to actually compute the exact angle. All right. So what I'll do over here is I'm going to redo this sketch, but I'm only going to focus on the displacement vector. I'm not going to write anything else out. And so coming over here, here's our x, here's our y, and I'm only going to focus on the displacement vector. So I'm going to take that, I can pick that displacement vector up, and I'm going to sketch it such that it comes out of the origin of my coordinate system. And so here is that displacement vector. That's delta r. All right. So all I did is I just picked this vector up here. This is our delta r, and I just picked it up and moved it to its own little coordinate system. Okay. And so this distance right here, this horizontal distance right here, that's the x part. That is negative 1.194 kilometers. And the x part of that vector is right there. That is plus 2.989 kilometers. All right. So now we want to compute the angle. Well, which angle do we want to compute? If we use our trigonometry unit circle notation, we can use arctangent to compute this angle right there. Now we have a problem. Arctangent, if you remember trigonometry, arctangent, when you use your calculator, is only going to work if you're in quadrant 1, this is quadrant 1, or quadrant 4. All right, so this is very important. Your calculator only works, when you're doing arctangent, your calculator only works with quadrant 1 and quadrant 4. So if you have a vector over here in quadrant 2, the trick you have to do is you have to flip it, extend this vector in this direction, right? So we just flip the vector over to put it into in this case, the 4th quadrant. And so then this piece right here, we flip the signs. This will be plus 1.194 kilometers, negative 2.989 kilometers. And now we get an angle with respect to the positive x-axis. All right, so that's what arctan on your calculator will give you, this angle, right? And so we want to know the tangent of this angle theta. Let me call this theta 3. The tangent of theta 3 is opposite over adjacent, so we want the opposite side, negative 2.989 divided by the adjacent side, 1.194. And both of them have a kilometers, but the kilometers cancel out. And so this is negative 2.503. So taking the inverse tangent of both sides, theta 3 will be the inverse tangent of the quantity negative 2.503. Okay? This is also called arctangent. And now you can use your calculator to compute that angle. And when we do it, we get theta 3 is negative 68.2 degrees with respect to the plus x-axis. So that's this angle right here. It's negative 68.2 degrees. The minus sign means below the x-axis. It means clockwise. Remember, clockwise angles are negative, counterclockwise angles are positive. So that's theta 3. And then from geometry, if we know theta 3, this angle is indeed the same in terms of magnitudes. It's the same as that angle right there. Okay? So if this is negative 68.2 degrees in terms of the magnitude of the angle, we know that these two angles have to add up to 90. So this angle right up here is 21.8 degrees. And so our final answer is going to be this displacement vector is 21.8 degrees. This is north, so we're a little bit west of north. So I will write this as 21.8 degrees west of north. Okay? So that's another way of stating our position vector. It's 3.23 kilometers in terms of its distance, and its horizontal range is 21.8 degrees west of north. We could also write that one other way. If we write this whole angle right here from the plus x-axis to the location of this vector, we're going to have to add 90 plus 21.8. Another way of writing that angle finally is, or we could write it as plus 111.8 degrees with respect to the plus x axis. And so that's how you compute a displacement vector in 3 dimensions.